Hi everybody, thanks for tuning in here. This is Mrs. Johnson and we're starting our 3.5 notes packet over rational functions. There's one thing that you need to remember, something from last semester. So remember the difference between the HOI and the VOX that we talked about when we're graphing lines. The HOI stands for horizontal, zero slope, y equals. The vertical lines are undefined slopes and they are x equals lines. So just keep those in mind, kind of have that in the back of your head as we're going through these notes. You do need to know what a rational function is. Remember, rational means fractional. So they're all a bunch of fractions, and if you kind of glance through the notes packet, we're graphing a bunch of fractions here. A rational function is defined as any rational function. I'll use r of x for rational function. It's any two equations, p of x and q of x, where p of x and q of x are polynomials. And remember, because we're dealing with fractions, the bottom polynomial, the q of x, cannot be equal to 0, just because it's a fraction and you know that we can't have zeros in the denominator. So we are going to go over several vocabulary words here before we start actually graphing these, and this whole section is over graphing all these different rational functions and how to do that. And there's a bunch of different steps that you're going to be responsible for understanding how to work your way through. The first new vocabulary word is a vertical asymptote, and we sometimes denote it VA. And what that means is it is obviously a vertical line. Let's see, that the graph cannot cross. Okay, the vertical line, remember you're thinking set the denominator can't equal 0. So you need to figure out what makes the denominator 0 in order to figure out what the vertical asymptote is. Also keep in mind there can be more than one. And we'll do an example later where there is more than one vertical asymptote. Okay, so for this very first example here, we're going to take, this is example number 1, we're going to take the denominator and we're going to set it equal to 0. And then when you solve for x, you end up with x equals 2. And that is actually our vertical asymptote. I'm going to dot that. If you have a different colored pen or pencil or a highlighter or something, it's useful to put that vertical line, which is x equals 2. So it's a vertical line through 2, and I'm going to dot it on my graph. And this serves as my line that the graph is not going to go through. So again, it's easy if you have a highlighter or a different colored pen or pencil to put the asymptotes on your graph. I like to think of asymptotes, since it's a new vocab word that we haven't talked about before, as an electric fence. My mom has an electric fence for her 2 poodles, and those dogs just want to get closer and closer and closer to the fence, but they will not go through it because you know they get a little shock on their neck if they go through the electric fence. So they want to go really close to it, but they don't actually go through it. So think of that vertical asymptote as an electric fence for your graph, and your graph is going to approach the vertical asymptote but never go through it. Okay? So that is step 1 for all these graphs that you're going to do, is figure out what the vertical asymptote is by setting the denominator equal to 0 and solving, and then dotting that line, very first thing that you do. Okay, we also have horizontal or oblique or slant asymptotes, denoted HA and OA. And there's several steps that you're going to have to go through in order to figure out what these are. So here's the definition: a horizontal or slanted line that the graph approaches. And there's different ways to find it based upon the equation that you're given. You have 3 choices. Okay, and again, it's just going to be another dotted line that we're going to put on our graph, but it's either going to be horizontal or slanted, and it's going to serve the same purpose. The graph is going to get closer and closer to it, but usually not touch it. And we'll talk about why I said usually much later in this packet. So the first choice is if the degree on top, so the polynomial on top, so in this case the x plus 1, if the degree on top is less than the degree on bottom, that means that your horizontal asymptote is the line y equals 0. And so in this case, the degree on the top is 1 because it's x plus 1, and the degree on the bottom is 1, so that does not fall into this category. This is actually category number 2, your second choice. If the degree on top equals the degree on the bottom, then in that case, the horizontal asymptote is y equals the lead coefficient of the numerator divided by the lead coefficient of the denominator. Okay, so in this case we have to look at our lead coefficients. So the degree is 1 for both the top and the bottom because they're both x to the first polynomials. So our lead coefficients is they're both just 1. Lead coefficient of the top is 1 and the lead coefficient of the bottom is 1. So we just found our horizontal asymptote. Okay, we'll do a couple more examples because this is a little bit of a lengthy process, but we just found our second red dotted line that's going to go on the graph. So I'm going to dot the line y equals 1. Remember, that's a horizontal line, hence the horizontal asymptote. And I'm going to put that line on the graph as well in a different color. And that's my second electric fence type of situation for this graph. Okay, the third choice for these horizontal or oblique asymptotes is obviously if the degree on the top is greater. That's the only other option that we haven't done yet. Is greater than the degree on the bottom. That's called an oblique or slanted asymptote. And you divide the polynomials using synthetic division. We keep using synthetic division over and over and over again, it seems like. Okay, and just know that this we're not going to talk about today. This is going to come into play later in the packet, so you don't need to worry so much about option number 3 here. We're going to get to that later. So we're just focusing on 1 and 2 for today. All right, so x-intercepts and y-intercepts, we have to do that as well. So this is all still the same problem, the same equation that we have at the top. So remember, this should be reviewed from Algebra 1. To find the y-intercept, that just means you plug in 0 for x and solve. So what is our equation way up here? It's still in the box here, x plus 1 over x minus 2. You're plugging in 0 for x. So 0 plus 1 over 0 minus 2. That's negative 1/2. That means that our y-intercept is the ordered pair 0, negative 1/2. And I'm going to put that point on my graph now. You notice that I'm updating my graph with each step that we go through. So 0, negative 1/2. It's about right here. Okay. Now we have to figure out the y-intercept, or x-intercept, excuse me. That means plug in 0 for y. Okay. Basically what that means, since we're dealing with rational expressions, is that means set the numerator equal to 0 and solve. Okay, that's the same thing as plugging in 0 for y because you cross multiply. So it's easier, it's a little bit of a shortcut just to set the numerator equal to 0. So our numerator of this equation is x plus 1. So I'm going to set the numerator, which is x plus 1, equal to 0 and solve for x. So you get x equals negative 1. That means that the x-intercept is negative 1, 0. I'm going to now update my graph again and put negative 1, 0 on the graph. So that is here. And I now have enough information because the awesome thing about putting these asymptotes on the graph is that you know what the shape of your graph is going to look like, because just like my mom's poodles, they are attracted to that electric fence but they never go through it. Okay, so you know that you're going to be connecting these 2 points here, and it's going to approach the asymptote and get closer and closer and closer to it and run up along next to it but never go through it. Okay, it's also going to be attracted to the vertical asymptote, so it gets closer and closer and closer but never touches it. So as long as you can get those intercepts on the graph and a couple extra points every once in a while, then you know the shape of the graph, because the asymptotes kind of are like magnets and it attracts the graph to get closer to it. Okay, so now I just need to have some kind of x value over here on the right hand side of the vertical asymptote, I'm going to check either x equals 3 or x equals 4 just to see what the other half of my graph looks like. So in order to find more points, let me come down here and have a little bit more room. Find more points. Like I said, I'm going to plug in at x equals 3, figure out where the y value is, just so I can get one more point and then I'll know what the shape looks like. So at x equals 3, I'm going to plug that into my original equation. So 3 plus 1 over 3 minus 2. That's 4 over 1. So the ordered pair 3 comma 4 is another point on my graph. And again, I just picked an x value that was to the right of my vertical asymptote, so I had some idea of what was going on this side. The ordered pair 3 comma 4 is right up here, and that actually makes the other half of my graph. So again, it's going to get closer and closer to the asymptote but never touch it. It comes down here and just kind of runs up alongside of it. Okay, so these are really weird and strange shaped graphs that we haven't really seen anything like before, but as long as you get those red dotted lines, those asymptotes on there, it's pretty easy if you just collect a couple points to figure out what the shape of the graph is going to look like, as long as you know that it acts like a magnet and it attracts the graph towards it. Okay, domain and range, just use the asymptotes here. It's basically all reals except for whatever the asymptotes are. So remember, for domain, it's everything except the x value of, what was that, 2? And how do you write that in interval notation? Negative infinity to 2 with a parenthesis, and 2 to infinity. And the range is everything except that, that horizontal asymptote, which was at y equals 1. So everything except 1. And again, how do you write that in interval notation? With the infinities and parentheses on the 1. So the asymptotes are the important part here for domain and range. And that's how we're going to determine our domain and range, is just by looking at those asymptotes. Okay. One other thing I guess maybe I should mention, just like for vertical asymptotes, how you can have more than one, you sometimes can have more than one x-intercept as well. Can have more than one. Okay. All right, let's go. We're going to flip onto the back and we're going to put a little bit of this to work, just kind of going step by step through this process. And you have all the instructions on this first page with an example to look at. So let's see what it looks like with some different rational expressions here, rational equations. All right, step 1, the vertical asymptote. Remember, that comes from setting the denominator equal to 0 and solving. So you get 4 equals 2x, x equals 2. And it's important here to not just write the number 2. It is a line, which means it is an equation, x equals 2. It's not just a number, it is a line, it's an equation. So again, I'm going to change to red again, and I'm going to dot that x equals 2, that asymptote, on my graph. And that just makes graphing so much easier once you have a couple points on the graph to tell what it's going to look like. All right, the horizontal asymptote, remember that was our 3 different options, and in this case, the degree on top is 0. There are no x's on top at all, so the degree on top is 0, and that means it's less than the degree on the bottom. The degree on the bottom is 1, because it's 4 minus 2x. So we're not using the coefficients this time. If you flip back over to the front, what we wrote down in this case is that your horizontal asymptote is the line y equals 0. Okay, so it's a little bit hard to see when I dot this, so that's why I like to try and extend it. But that means it's the x-axis, okay? And that's because the degree on top is less than the degree on the bottom. It will always be 0 in that case, okay? Let's see, y-intercept, so just plug in 0 for x. So it's going to be 6 divided by 4 minus 2 times 0. So 6 over 4, which is 3/2. So that's the ordered pair 0, 3/2. So that's just plugging in 0 for x. That's all we did there. And I'm going to put that dot, that ordered pair, on my graph here right away. I'm updating it as I'm filling in my chart. Okay, x-intercept, that means set the numerator equal to 0 and solve. So 6 equals 0. Wait a second, that doesn't make sense. Oh, Okay, that means that there is none. There is no x-intercept. Okay, so sometimes that'll happen. Doesn't mean you've done anything wrong. It just means that the graph does not cross the x-axis. And doesn't that make sense since it's an asymptote there? So that's actually good. Okay, so what that means is I can already sketch the top half of my graph. It's going to go through that point and then approach the asymptotes but never cross them. So I need to do some kind of an x value over here. So I'm going to test x equals the asymptote's at 2, so I could do 3 or 4, it doesn't matter. I'll do 3 again. So when I plug in 3 for my graph, for my x value, I get 6 over 4 minus 6. 6 over negative 2. So that means negative 3. So at the x value of 3, I get a value of negative 3 for the y. Okay, which means it's down here. So you want to have at least one exact point on your graph, and then the asymptotes do the rest of the work. So that means that this poodle is going to run this way and get close to the fence, and this poodle is going to run this way and get close to the fence but never touch it. Okay? Domain and range, again, so that's everything except the x value of 2 is where our vertical asymptote is. The range, everything except 0. That's where the horizontal asymptote is. So in that case, you just write it in interval notation again. And again, using parentheses instead of brackets because it does not touch the value of 2. It gets really close to it but doesn't go through it. And negative infinity to 0, 0 to infinity. Okay, so not very many points in ordered pairs actually go on the graph, but the asymptotes definitely have to go on the graph, and it helps guide your graph and shape it as you go. Okay, last example we'll do for today is number 3. If you want to pause the video and actually give this one a try yourself and then check the answers, that would be an awesome idea. But I'll continue explaining if you choose to just listen and follow along with me. Okay, vertical asymptote again comes from setting the denominator equal to 0. That is step 1. So we end up with x equals negative 1. And I'm going to put that on my graph immediately, a dotted line going through x equals negative 1. It's really important, you guys, to remember the difference between horizontal and vertical lines here. You don't want to put a horizontal asymptote at negative 1 in this case. That would throw everything off and you would come up with a crazy graph. So really pay attention to the I guess the difference between the vertical and the horizontal here. It's very, very important. All right, horizontal asymptote. Let's see the degree on the top of this equation. I'll erase this and get it out of the way. The degree on the top is just 1, and the degree on the bottom is 1. So in that case, we use the lead coefficients. And remember, if you want to write these in descending order, like normal polynomials typically are written, it looks like this. They mean the same thing, but it's important to remember that those lead coefficients are negative 2 and 1. So since the degree on the top equals the degree on the bottom, it's y equals the lead coefficients, which is just negative 2 over 1, which is negative 2. Okay, that's option number 2 on the front sheet that we talked about. So I'm going to put negative 2 on my graph right away, a horizontal line there, and that's serving as my horizontal asymptote. Okay, so I got my 2 asymptotes. Those are, in my opinion, the most important part of the whole graph. Okay, now let's do y-intercept. So plug in 0 for x. So 6 minus 2 times 0, and 1 plus 0 is just 6 over 1. So that means that the ordered pair 0, 6. Remember you plugged in 0 for x and we got a y value of 6. So I'm going to put that on my graph now. 1, 2, 3, 4, 5, 6. A little bit off the graph, that's okay. I'll just put it right up here. Now let's find the x-intercept. That comes from setting the numerator equal to 0 and solving. X equals 3, that means the ordered pair 3, 0. Okay, so these are all just the step-by-step instructions from the front sheet of paper where we did all that writing. It does take a little while to get all of this stuff memorized, but every single problem is going to be very, very similar to this step-by-step process, okay? I'm going to put 3, 0 on my graph here. And now I know what the shape of the right-hand side of my graph looks like. It's going to go through both of those ordered pairs, and it's going to get really close to the fence but never touch it. Run right up alongside of it. Okay? Now I just need to come up with, I need to test one of these x values over here on the left-hand side of my vertical asymptote so I can have an idea of where that graph is going to take place. So in this case, I'll test the point, I'll do -3 again. You could do -2, -3, -4, -5, any of those values, just trying to get an idea of where the graph is going to take place. So I'll do f of -3. So I'm plugging in -3 to my original equation. So 6 minus, that would change it to plus, over 1 minus 3 is -2. So again, just plugging it into this original equation here, I get 12 over -2, which is -6. So the ordered pair -3, comma, -6, 1, 2, 3, 1, 2, 3, 4, 5, 6 is down here somewhere. Maybe not the best size grid I could have done for this example, but our graph is going to look something like this down here. Remember, getting closer and closer to the asymptotes, but never going through it. Okay, so a couple important things here is to remember to put arrows on your graph. Notice how all of our graphs have arrows because they get really close to the asymptotes but never go through. This one actually looks like it goes through, doesn't it? That is a little bit inaccurate on my part. So just be aware that we are going to be a little bit picky. You can't just put an arrow that looks like that, okay? Because that implies that it goes through the asymptote. So you have to actually show it getting really close, but not going through, okay? So just be aware of that. Domain and range, everything for all the x values except where's our vertical asymptote? -1. So -infinity to -1 and -1 to infinity. And then our y values, everything except -2. So -infinity to -2 and then -2 up to infinity. And that's our domain and range. Okay, that's it for today, guys. Go ahead and get started on that worksheet, see how far you can get, and make sure you bring your answers or your questions to class tomorrow. And I'll see you soon.